Precalculus lesson 10 point, did it again. Sorry, lesson 12.5. All right, 12.5. This is sigma notation and the nth term, or just sigma notation for short. So this is 12.5 sigma notation. Oops, I don't know why I did that other than I'm at the top of the page and weird stuff happens. Sigma notation. This is something that shows up profusely in math. It's just a very compact way of representing something, a variety of things that happen at kind of set in a set pattern. And this is one of those kind of things where I think it's most helpful just to give some examples for you to see how it works. So sigma notation is based on the capital letter sigma. Looks kind of like that. Okay? Lowercase sigma is like that. That shows up a lot, especially in statistics for standard deviation. But here, capital sigma. And here would be an example. Might be something as simple as like the sum from n equals 3 to 7 of 2n minus 1. All right, now here's what this means. Sigma, it's used to represent sum. So what we're finding is the sum of, and this is how this would be read. This would be read the sum, okay, that's basically the sum, okay, from n equals 3 to 7, that would be that and that, of 2n minus 1. That's how you would read that, okay? The sum from n equals 3 to 7 of 2n minus 1. And here it is in its expanded form. Basically, it means start with plugging in the bottom n value into the expression 2n minus 1. So this is going to be 2 times 3 minus 1 plus, then you go up integer values from there, plus 2 times 4 minus 1, because now we're plugging 4 in for n. Next, we're plugging 5 in for n, so that'd be plus 2 times 5 minus 1, plus 2 times 6 minus 1, plus 2 times 7 minus 1. So what do we get? We get 6 minus 1 is 5, plus 7, plus 9, plus 11, plus 13. Little hint that we'll see later. Whenever you have this 2n going on, you have values going up by increments of 2. So when we add these up, we have 5 plus 7 plus 9 plus 11 plus 13, we get 45. We get 45. So you'll have some problems where what you are given is this, and you're asked to write it in its expanded form. That would be like this line here. Write it in its expanded form, and then find the sum. That would be like this final answer. Okay, so kind of two parts to that. Expand. That would be like again like this, and write and find the sum. That would be like that. All right. So might not need it, but maybe I'm not even gonna bother with a quick another example of dealing with that because it seems pretty straightforward. I don't know what other questions you might have. Yeah, so I'm just going to leave it at that for now. But then what you also have, and this is where it can take a little bit more work and a little bit more experience, is being given an expression in its expanded form and figuring out what would be a way of putting it in sigma notation that works. And there are a few things that we'll see that are some tips that you can work off of. So let's say we have this. Let's say we have this. Something like express using sigma notation. And the first one, let's do this. 8 plus 10 plus 12 plus dot dot dot. 8 plus 10 plus 12 plus dot, 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 plus, we're going to go up to 24. So we're going to stop there. Okay, well, what I identify first is increments of 2, right? We're going up 2, and then we're going up 2 again. Whenever we're going up in increments of 2, I say, ooh, I have a 2n going on. In some shape or form, I have a 2n going on if I have increments of 2. All right, so I know that that's one thing. Now let's see what else we can do. Well, could I? Now you can start these wherever you want. So I could say, let's say, well, if I want 2n to end up giving me my first term, which is 8, could I start at n equals 4? Now let's see if that works. And this is kind of a go with something you think and then test it a little bit. So 2 times 4 is 8. So my next one would be 2 times 5. Okay, cool. Then my next one would be 2 times 6. And I'm going up to 12. So from n equals 4 to 12. And that would actually work. Okay? You could do something like this. What if you just like to start at 1? And you're like, you know what? I just like to start at 1. Well, you could still say you have 2n, but then what do we need to add? If n is starting at 1, you're at 2, so we need to add 6. Let's see if this would work. So in the first term would be 2 times 1 plus 6. That's 2 plus 6, which is 8. The next one would be 2 times 2 plus 6. That would be 4 plus 6, which is 10. Next one would be 2 times 3 plus 6. That's 6 plus 6, which is 12. And then we're going up to what n value? Well, you could just set it up and say 2n plus 6 equals 24. What does n need to be? And you could solve for what n value is where you're going to end. So that'd be what, 18? So then n is 9. So we're going from n equals 1 to 9 of 2n plus 6. As you may have deduced, there are an infinite number of ways that we could set this up. I just went with the 2 here that seems maybe the most likely to be chosen. Okay, let's do a couple more where some different kind of patterns show up. How about... No, that one is a similar thing. That one is kind of similar. Yeah, let's go with this one. How about this one? 1/5 plus 2/7 plus 3/11 plus 4/19 plus 5/35 plus dot, dot, dot. That means it goes on ever. That goes on forever. So we're going to have a to infinity and beyond. All right, let's look for a pattern. First, let's check for whether or not there's a set amount that is increasing, set increment. So we're going up by 2, so that's plus 2. Then we're going up by plus 4. Then we're going up by plus 8. Then we're going up by, let's see, 35 minus 19. 35 minus 20 would be 15, so we're a plus 16. Well, there's no set increment, but it's interesting. We're going up by powers of 2, right? 2 to the first, and then is 2. 2 squared is 4. 2 cubed is 8. So I have, in some shape or form, a 2 to the nth probably going on. So I'm going 2 to the first, 2 to the second, 2 to the third for what my increments are. But it's not the actual values themselves, so I'm going to have to tweak it a little bit. Okay, so I appear to have that going on. What do I have going on top but just n, right? If I say from 1 to infinity, and I just have n in the numerator, so I have n in the numerator. Now let's see what I need to do to a 2 to the n in the denominator to give me what I want. If I'm starting at 1, so I'm dealing with the sum from n equals 1 to infinity. So that n equals 1 with the n on the numerator will give me 1, 2, 3, 4, 5 in the numerator. But then 2 to the first would be what I currently have. So how can I tweak my 2 to the first and turn it into a 5? Well, if I add 3, that would do it. But the question is, will this continue to give me the pattern that I want? So the second term would be 2 squared plus 3. That would be 4 plus 3. That's 7. The third term would be 2 cubed plus 3. 2 cubed is 8, plus 3 is 11. Then the fourth term would be 2 to the fourth, which is 16, plus 3, 17, 18, 19. Sweet, it works. So this could be represented as the sum from n equals 1 to infinity of n over 2 to the nth plus 3. Okay, let's do one more. Let's do this one. Let's go with 4 minus 9 plus 16. 4 minus 9 plus 16 minus 25 plus dot dot dot. Okay. So one thing that we see that the sign is reversing every time, right? We're going positive, negative, positive, negative. Well, when that is happening, when you're switching from positive to positive to negative each time, we can represent that in some shape or form by like a -1 to the nth, some negative number to the nth power. Because what this makes is it makes it whenever n is even, we get a positive number, and whenever n is odd, we get a negative number. Okay? All right, what else do we see? We see that, we have perfect squares, right? 2 squared, 3 squared, 4 squared, 5 squared. Okay, but we're starting with 2 squared. So I could just say, how about we deal with the sum from n equals 2 of, in some shape or form, n squared, right? Because that would get me starting out at 2 squared and then going on to a 3 squared. Okay, so n squared, but then I have this switching back and forth, but I'm starting at an even number and I'm starting at a positive. So can I just do a -1 to the nth tacked on there? Well, let's see what that would give me. That would give me first a -1 squared times 2 squared, right? Plus -1 cubed times 3 squared plus -1 to the fourth times 4 squared. And what would this become? The -1 squared is positive, so this becomes a positive 4. This becomes a -9. This becomes a positive 16, and that is matching. So it's doing that to infinity. To infinity. All right. I think I said one more, but I haven't given you any that involves factorial. I want to give you something that deals with factorial. I'll tell you what, to give you a sense of dealing with factorial, let's look at number 43. Oh, does that have factorial? Ooh, yeah. Let's go with that, actually. Not number 43, different one. Let's go with this. Let's represent in sigma notation 3 over 9 times 2 plus 8 over 27 times 6 plus 15 over 81 times 24 plus dot dot dot. All right. So factorial comes up sometimes. It actually comes up a lot in the context of sigma notation, depending on the context. So factorial, it's helpful to know what the pattern of numbers is. So what we have is well, 0 factorial is 1 for the same reason that something to the power of 0 is 1. I'll explain more of that in just a second. 1 factorial is 1, 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, so that's 6. 4 factorial is 4 times 3 times 2 times 1. Well, 4 times 3 is 12, times 2 is 24. 5 factorial is 5 times 4 times 3 times 2. Let's see, 5 times 4 is 20, times 3 times 2. 3 times 2 is 6, so 20 times 6 is 120. And then we do that times another 6, and we get 6 factorial is 720. And that gives you enough. But mainly, note this 1, 2, 6, 4 that's going on. 1 factorial, 2 factorial, 3 factorial, 4 factorial. 1, 2, 6, 24. Okay. For the whole 0 factorial, if you did 2 factorial, well, let's see. I'll say this. 3 factorial divided by 3, that's the same thing as 2 factorial, which is what? Well, what's 3 factorial over 3? But that is 3 times 2 times 1 over 3. Those cancel, left with 2 times 1, right? Which is 2 factorial. Okay, 2 factorial over 2 would give us 1 factorial. What's 2 factorial over 2 but 2 over 2, which is 1, okay? Which is what 1 factorial is. Well, 1 factorial over 1 would give us 0 factorial. 1 factorial is 1, 1 over 1 is 1, and that's why 0 factorial is 1. All right, that's just a little to the side. Okay, back to this one. So what I see is here I see a 2, a 6, and a 24. And I see 2, 6, 24. So I see factorial going on. Okay? So in particular, I'm sorry, I have 2 factorial, 3 factorial, 4 factorial. So maybe I can start at n equals 2, and I have an n factorial going on in the denominator. Let me put that farther to the right, because that's the one I'm dealing with. The right-hand side of the denominator. All right, what else do I have? I have 9. Well, 9 is 3 squared. 27 is 3 cubed. 81 is 3 to the 4th. So 2, 3, 4 were my exponents there. So here I have 3 squared. Here I have 3 cubed. Here I have 3 to the 4th. So it looks like I have a 3 to the nth going on, where again I'm starting at n equals 2. Okay? Then how about this numerator? Well, I had jumped to me what I'm pretty sure it is, but let me look at this first. So 3 to 8, we're going up 5, right? 8 to 15, we're going up 6. No, 7. Duh. We're going up 7. I'm not finding that super helpful, but, and here's what I first noticed, and just keep an eye out for this. Keep an eye out for numbers that are like some set amount above or below perfect squares. So in other words, 3 is 2 squared minus 1. 8 is 3 squared minus 1. 15 is 4 squared minus 1. So I see an n squared minus 1 going on, where again n starts with 2. So n squared minus 1. Let's see if this checks out. So let's try when n is 2, so that gives me 2 squared minus 1 over 3 squared times, so this is n is 2, times 2 factorial. That's a 2 factorial times 2 factorial. And I'll oftentimes like to do n equals 2 just to remind myself. So now I'm doing n equals 3. So that would be plus 3 squared minus 1 over 3 to the 3rd times 3 factorial, and then when n equals 4, I have plus 4 squared minus 1 over 3 to the 4th times 4 factorial. And let's see if these simplify to be what I started with. So 4 minus 1 is 3, the numerator is good, 3 squared is 9, and then 2 factorial is 2, the first term checks out. 3 squared minus 1 would be 9 minus 1, or 8, over 3 cubed, which is 27, times 3 factorial, which is 6. And then my third term, I have 4 squared is 16, minus 1 is 15. 3 to the 4th is 81. 4 factorial is 24. So yep, this checks out. So we have that. Oh, except I got to include the sum from n equals 2 up to, it's a dot, 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 so to infinity. N squared minus 1 over 3 to the nth n factorial. Okay? That should do it for you. Let me know if you have questions, and I'll see you next time.